I'm Chris Wilkinson. I'm the Director of Planning and Architecture for Internet 2 Network Services. And I'm going to sort of lead a combination of a short talk and a roundtable in this during this session. We had such a great team, and there's so much work that's been done to bring this the NGI platform to fruition that I wanted to give a number of folks an opportunity to speak. And so give me just 1 second. So I'm going to start today by just touching real briefly on the use cases for NGI. Rob went through those in detail, so I'm certainly not going to repeat that content. And then I want to sort of do a walkthrough of the sort of as-built status for the platform. We've gone through a whole bunch of different talks over the last few years about what we were going to do. And now, of course, that's actually happened. So I want to just run through an overview of what we built and how we built it, and whether or not we stuck to our original design principles for all these areas. Route policy was a big area. So Jeff Bartig's going to walk us through some of the process that we went through to get our route policies transitioned over to the Cisco network. Camille's going to talk a little bit about space and power, and then the group of us will go on through peering, transition, AL3S, community facing, AL2S, and then the optical transition. And then we'll do a short wrap up to kind of talk about what we're thinking about going forward. So the three use cases that I'm going to focus on in this talk are the data intensive research use case, enhanced cloud access, and the sustainable economics. We'll do other webinars and future talks on infrastructure sharing, and Mike Simpson and Carl will of course talk about software driven infrastructure. I'm really going to focus on the platform and how we migrated onto the platform, how we transitioned services onto there during this talk, and we'll do some follow-ups on all these in the coming months. So excited to pull up the worldview this morning. This is the NGI platform. I believe this is visible publicly on the NOC website. This shows very clearly that traffic is on the NGI platform. As you can see, from sort of blue through green to yellow through red to purple. So these maps are originally designed to be a capacity management tool, but they give a good feel for how busy the network is and how busy a given link is. A couple of interesting things here that you can kind of see, in addition to some traffic levels, you can also see our link topology, which is defined by the architecture that we had to employ to use the disaggregated hardware. And I'll talk a little bit more about that in some future slides. But the main thing I wanted to point out here is just what the general traffic levels were. So some of these annotations already exceed some of the previous link capacity that we had on the legacy network. So for example, Raleigh to Ashburn is up above 110 gigabits per second most days. That previously was a 100 gig link. And all throughout the platform, there are links that are already running above 100 gigs where there was only 100 gig previously. So I think we could say that in some ways this was a just-in-time upgrade, which we definitely suspected, but that's definitely become fruitional and real as we've headed into the fall semester and on into winter. So network very actively used. In Chicago, there's a link that I saw that was peaked at 170 gigabits per second. Presumably, for example, that's BTAA heading towards Equinix Chicago. The one out of Kansas is, of course, GPN heading towards Chicago. 110 out of Raleigh is presumably MCNC. So network definitely under active use. And because all of our services are transitioned, it's easy to see why. There's a few things that aren't. This, of course, is all running on this disaggregated compact platform. Camille will talk a little bit about, kind of the power and colo savings that we have on this, but this is running on the gear shown. This in this case is New York. Sienna's on the left, 14 slot, compact chassis, wave servers on top of that. On the right, a couple of 1U Cisco 8201s, very common at all of our three-way sites, this type of configuration. Versus the old network, again, just a quick snapshot, 4 racks of Sienna, full racks, 1 half rack of Juniper chassis. But let's take a look at the traffic levels on the legacy network. So this is another world view of the legacy network. A few of these links go between dark blue and the lightest shade of green. As there are a few lingering peers in Los Angeles, there's a few services that are still, sort of corner cases that we're moving. But for the most part, this map stays blue, occasionally kicks up to a little bit of green. One other really neat thing to note here is that the missing links on the topology are not map errors. Those are actually links that are being taken out of service as the previous platform, the MX platform, is decommissioned. So not only is the map light on traffic, it's also starting to show where we're beginning to pull the platform down. So again, pretty exciting to see both those maps. You can check these out on a world view. I believe they're accessible. So each of these links that was shown on the previous NGI map are built on these primary building blocks. There's some variance depending on services, but for example, all 400 gig services on the map are built with this ROADM topology, 6500 FlexGrid ROADM, Sienna Wave Server 5s. This is a point-to-point example. A few things to note: it's all EDFA. It's all ultra fiber everywhere where ultra fiber was available to us as part of our ARU. So there's 100% consistency aside from a few places where there was a little bit of leaf where ultra wasn't available. But this is the topology that the 400 gig platform is built on. Moving down to the lower diagram, this is the services hierarchy for most of our AL1S services. So the Wave Server 5s here are shown here. The line system is in the middle. The Ciscos are out here on either side in red. Basically, a 400 gig circuit is generated and managed by the Wave Server 5s on either side. Because across the platform, we can achieve above 400 gigs. We're also multiplexing, for lack of a better term, other services into that same wave. So there's 100 gig community services running through here in green. There's blue on blue, there's 10 gig community services all running through this platform, common line system, common Wave Server 5 infrastructure. As I mentioned, there's a few corner cases where we had a circuit, but not a Wave Server 5, but this is repeated across the entire platform. And this was the original design intent through the optical RFP, and it's exactly what we built and are operating today. Rob did mention that we're achieving, higher than 400 gig rates. That's good. We have a lot of services that we wanted to carry on this platform. So for all of the links that we have in service, we are achieving that 600 gig line rate. That means there's always excess capacity, if you will, or assigned capacity on the wave that can carry the 400 gig backbone, but also can carry these 100 gig and 10 gig services alongside. Every single link in the network is carrying those services every place where 10 gig goes. And if there isn't a 10 gig service, then it's carrying an available 100 gig. So just to show that the platform can burst, this 400 gig in our testing regime, we did run some tests with the Viavi from coast to coast. This is across the packet platform. This is not across a wave. So, Viavi installed in Washington, DC, loopback installed in Los Angeles, tested coast to coast through multiple hops of the packet platform. There wasn't a lot of traffic on the platform at this time, so there wasn't any disruption. This was sort of a pre-migration step that we did, but it does show pretty strongly that the platform is capable of performing as we'd expect. We won't really know until we load and scale and get down the line, but initial results are good. that the platform does perform as we expect. More on that as we go. Famous last words, maybe, hopefully not, but so far so good. So I just wanted to talk a little bit about sort of how the Ciscos and the Wave Server 5s connect. So we made the choice through the RFP process that we would work with AOC cables to help keep costs down throughout the platform. So there's 188 links that have AOC cables on them. And so each of these, the Cisco here is in red, is connected to the Wave Server 5 module at 400 gigs through this AOC cable. They're actually 8-lane AOC cables, which means there's 8 different optical signals that all come through that cable, come out of the Cisco and vice versa into the Wave Server 5 module. And you know, in a normal world, this is bit error rate on the left over time. This was a sample that we took for about a month on a bunch of our cables to see if they were performing. We saw a few sort of link anomalies on the platform, and we wanted to investigate what those were. And so we started doing some in-depth analysis. Andrew Lee did a lot of work on this for us, and then we've continued the analysis as we went. So just wanted to show another part of the system that comes together to form a successful link between cities. Based on all these building blocks, we built a topology here on the left. And so Rob showed this. Each of these single lines is 400 gig. Each of the double lines is 2 by 400. One of the goals in support of data intensive research was to have this 2 by 400 minimum connectivity from each node. So in the case of Phoenix, you do have 400 gig east and west. In the case of the other metros, you may have 2.4 gigs of exit capacity from that metro. Some of them even scale up to 3.2 terabits per second. So you know, there's massive scale out of some of these cities. This inset that I have here on the left is Los Angeles. And you can see here that heading towards Sunnyvale, there's 800 gigs of backbone capacity. There's 400 and 400 and 400 in case of Salt Lake, aggregate 800 the way that's structured. And some of this was done for efficiency. Some of these smaller sites have a single 8201 chassis. These larger sites have multiple 8201 chassis. Peering sites have multiple 8202 chassis. And so depending on the nature of the site and the connection requirements, the chassis type was changed depending on, or the chassis configurations was changed depending on this nature of the site and the other requirements of the location. So this in blue also shows how those locations are meshed. So if a site, if a site has 2 chassis at a site, they're connected separately to the 2 chassis at the adjacent site. And there's a reason for that. One is resiliency and redundancy. The other is, you'll see in a moment, it helps out to ensure that peering traffic and cloud traffic can flow between locations as efficiently as possible. But every site that has 2 8201s is connected, dual connected to the adjacent sites with 2 8201s. And in where we could, we attempted to separate those out onto separate wave server modules so that, you know, we were minimizing potential points of failure. The other thing it does is it provides a large number of edge ports in 400 and 100 at all these locations. Rob mentioned that you know, each device carries 24 by 400. So in a location where there are 2, there's 48 by 400. Some of those are taken up by backbone, of course, and other services. But that's the total number of ports that were available. And the number of backbone ports that are consumed are not actually that many of that 48 in this case. You know, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here out of 48. There's still 38 ports in Los Angeles that are available to be used going forward. Another big change that was made as part of NGI was a standardization of all of our interconnect locations. So the interconnect locations are the primary places that we pick up PNIs to external providers, public exchange connections, as well as all the AWS and GCP and other providers as part of Cloud Connect. Our goal, there are 7 peering locations, was to make these all 100% standard, effectively have them on net. There were a few places where the topology sort of encouraged the backbone and the peering location to be separated. Where that happened, we effectively distributed the functions of the location out across 2 sites. This was in our original plan. It has played out that way. And this is, for example, how Dallas, Los Angeles, for example, are built, Sunnyvale as well. And so in this case, San Jose, for example, is where the cloud edge devices are. These are 8202s up here on the upper right. These are 8201s on the lower left. They're in the Los Angeles Lumen POP. And there's metro connectivity between them. Each of these blue lines is 400 gig. So it's a total aggregate of 1.6 terabits between the locations. This is effectively scalable, not infinitely, of course, but it's fairly easy to add additional 400 gig capacity between these devices in 400 gig increments as demand increases. That really goes for any of this topology shown previously. It's fairly easy to scale those upward by adding Wave Server 5 chassis, which we left space and power for in the locations, and of course, adding router ports as well, or adding connectivity into the router ports. The other big change that we made was sort of this assured load balancing for all cloud peers. So this diagram in the red and the green is intended to show sort of egress out of the peering location. No matter how because of this mesh topology, no matter how a stream comes out of a cloud peer and hits the edge network, it has an equivalent cost to go out. So if we follow red in any of these sort of path, we get an equivalent, for lack of a better term, cost out here. So in the case of a failure or any number of other conditions, this situation continues to be fairly well assured. There are ways, it's a complex topology where you could end up with that not being the case. But the goal was to have this load balancing, which is really key for AWS and Azure and those services. It's a requirement for many of them in place at all of our cloud peering locations. Previously, it wasn't entirely consistent that was the case. And so this was a big change as well that we were able to ensure we got through. So stepping back a little bit, one thing that we did find was we saw some subtle link fluctuations in some of our 400 gig links. It's a very new technology. It is out there. Deployments like ours are not very commonplace, especially involving 8-lane AOCs and other technologies. So when we took a look at this, again, this is that same sort of bit error rate over time. We noticed on a couple of our links, a fairly small number, that there was a variance in some of our lanes. So here we have a single lane on our 8-lane AOC that has a higher than typical bit error rate. So most of us, in our experience, start looking for the issue. Is there a client settings issue? Probably not in this case. That would be causing link fluctuation. Is the AOC damaged? AOCs are, MPO, they're multi-fiber. Is the AOC damaged? Is something going on? In this case, no, we replaced AOCs and the problem continued. Is something out of spec about the AOCs? We actually saw this in another use case in our platform with PAS. We had some cables, in this case DACs, that were out of spec. But is something out of spec? Again, in this case, no. What we did find is that there's a lot more to this equation than just a cable. There's electrical timing, there's DSPs, there's a whole bunch of stuff that's engaged in the platform to bring these 400 gig links to fruition. And, for example, the clock timing and all that stuff on 8 lanes has to occur perfectly correctly. So one of the things that we traced this down to was an electrical timing issue on the Wave Server 5s. Now, this was an addressable issue. because it was ASIC based and that there could be a fix applied to that. But it was a really interesting revelation that at these bit rates, at these speeds, even the slightest timing issue on a single lane is still going to cause issue to come through. And so we have a fix for this. It's being rolled out. But it was I just wanted to kind of step back and show that, early adoption definitely, gives us a lot to think about in all these cases. And we saw this throughout other issues in the platform as well as we deployed it. Unfortunately, we don't have a lot of time to go into that today. But just wanted to kind of take a step back and show that. So with that, I'm going to hand off to Jeff, who's going to talk a little bit about route policy, which was another really important thing that we had to get right to make this happen.
Okay, Chris, can you refresh the slides? Maybe just restarting the presentation. Yep. So about a year ago, we started about a year ago, we started looking at how we were going to handle route policy on the NGI network. We were just starting to get access to the 8000s in our labs, being able to play with them a bit. A number of us were working on refreshing our knowledge of iOS XR since we had been using primarily Junos for quite a few years. And we were looking at the challenge we had. Looking at the MX network, we had 52,000 lines of route policy that existed in the MX router configurations. Most of this configuration was manually created by network engineers typing at a CLI over time. How the policies were created and implemented evolved over the past 20 years. There were a lot of customizations that were done. There was a lot of small mistakes that might get introduced or small differences in the policies that get introduced as different engineers over time turn up new peers, new neighbors. And we found there was little documentation on why some things were done in some ways. V4 policy differed from V6. And then we were also looking at the challenge of how do we work with NSO? How do we get NSO to handle our configurations, help us deploy them? And our experience with NSO a year ago was just starting. So we had some goals though. We wanted to standardize things. We wanted NSO to be able to deploy the configs. We wanted to hopefully completely eliminate any need to go onto a router and manually configure any route policy. Yet we still wanted to allow customizations to be done and handle things like what if we need to do traffic engineering with a I2PX peer. We didn't want templating to get in the way of being able to accomplish what we needed to do. So next slide. So one of the first things I did was, as I started working on the route policy, was I took a look at what the current best practices were and recommendations from the greater internet community. And I ended up creating an initial basically template that ended up driving all of the rest of the configurations that I created. What I've got on the screen here on the left is a textual description of what I generated looking at these best practices. On the right is actual route policy off of one of our routers today. This route policy and the description on the left is looking specifically at I2PX participant policy. And so this is what is used on every single participant neighbor for the I2PX service. Couple of key things I want to point out is how we do, and I'll cover them in the next couple slides, is selecting routes, how we handle exceptions, and how we handle maintenance. Chris, the slides are bouncing between slides on me. Can you go back a slide? And how we handle exceptions, and lastly, how we handle maintenance processing. But iOS XR has a really nice route policy language. It's out of all the routers I've worked with, I would say it has one of the probably the nicest policy language. It's very readable if you choose to make it so. It allows comments. I'm sorry, but to fit the policy I have on the left on the screen, I actually deleted all of the commenting that we have in here that explains what's happening. But commenting is very helpful. And it has nice if-else type structures that can be used. We found that it also allows us to pass in parameters to policies, and those parameters can actually be other policies. And so that helped us to simplify some things and do some creative things with our initial set of policies that we have. Looking through this particular policy, the first thing we do is we select routes we want to accept. We drop bad routes, things like bogons, internet to zone internal prefixes that we never want to see come from the outside world. We try and do some protection against route leaks by filtering tier 1 ASNs and paths. We strip out BGP communities, our own internal BGP communities, so the outside world can't mess with our routes. We do remote trigger black holing, drop prefixes longer than our policy. The policy does include the ability to drop our PKI ROV invalids. But we currently are not, we don't have that enabled. We then set defaults that are expected, things like BGP communities, default local preference. We allow local preference to be overridden on customer routes. And then we handle exceptions and maintenance. Next slide. On the left here, which you'll probably hear about a lot more later this week, is our NSO configuration for an I2PX participant. I included here just to show what the network engineers are actually now configuring, rather than jumping into a router and configuring interfaces and BGP neighbors and route policy and prefix lists. It's all handled in NSO now, and the engineer types commit at the end, and the config gets pushed out to routers. Reason I include it here and talk about route policy is I wanted to show where some things are coming from. The route policy on the left is basically static and used for all of our I2PX participant neighbors on the network. The NSO, though, dynamically creates a couple of additional policies. It creates a selection policy that's driven by the prefix lists that are listed in the NSO service for this for I2PX. And if there are any exceptions, it'll create a custom policy that includes those exceptions. And this is where we can add some deviations from what the policy would normally do. This particular example I have up on the screen on the left, there's some exceptions here that will set a BGP community on all routes, actually 2 different BGP communities. This particular example is of a participant who only wanted to receive routes from Amazon from their I2PX BGP neighbor. And so these allow us to basically drop anything that isn't an Amazon route and set BGP communities on the routes that this participant is sending us so that they only get sent to Amazon. And those NSO dynamically creates policy, and then that policy gets executed on the right at the appropriate place. Next slide. The other thing that I was really happy about with what we ended up being able to do with NSO is we have this idea of the admin state for all of our services. The admin states I want to mention here is this service is currently in service. That means it's been deployed onto the routers and it's accepting routes and operating as normal. We can change the admin state in NSO for any of our services, and we can do this for a particular I2PX service for a specific participant, like I show here on the left. We can also set the admin state on an entire router, or if we have a public peering exchange, we can set it for the public peering exchange. And if maintenance state is set on, or an admin state of maintenance is set on an entire router, it will actually take action for all of the neighbors. The admins or the maintenance state gets passed into the BGP policy up at the top, and at the very bottom of the policy is where that's acted on. And if we go to the next slide, so we have 3 different maintenance or 3 different states that this policy looks at. And we have similar policy for all routes on input that we receive from neighbors and on output routes we export to neighbors. And so if this policy receives a state of 0, it's considered in service, and it's basically a no op. Just ends and doesn't take any action. But if a maintenance state has been requested either for this neighbor or for the entire router, then additional actions are taken. If it's pre-maintenance state, level 1, we depreference the routes. We set local preference to 0, set meds as high as they'll go. We add prepends, and we tag the routes with the well-known graceful shutdown BGP community, which will notify downstream people who receive this route that this route may be going or should be going away soon, so they may want to take some action themselves to depreference the route. Going into pre-maintenance and making the route look less desirable, but not completely withdrawing it, allows routers that receive these routes to dynamically find a better path before the route disappears completely. And finally, level 2, actually going into maintenance, does a drop of all routes. And so when we're going to do maintenance on a router, we can now go into NSO, put the router into pre-maintenance, wait a few minutes, then move the router into maintenance. And by that point, traffic should have been shed from the router and we can safely work on it. These maintenance policies have been deployed now on everything in the I2PX VRF on the network and the RNE VRF. And so these features are available for us there. The BGP graceful shutdown community is supported in both networks now. So if connectors want to send us the graceful shutdown community, indicating they're going to be doing maintenance on their network, we will depref the routes and try and find a better path. So, and moving on to power and co-location, we have Camille.
Hi. Okay. Welcome. So when we started out the project, there was a lot of talk about how do we come up with efficient and creative rack solutions. There was much discussion like, can we fit everything into one rack, one cabinet? And that was the goal. We weren't able to do that in some locations, but quite a few we are. And so we decided we need to look at every RU of space within a cabinet as being valuable, and that's what we've done. So some of the things that we have looked to do is we started at the bottom of the cabinet and we built up. So therefore, the longest of the power cable runs were the first to be installed. And that allows for efficient use as we're coming up and we don't have to worry about like wasted RUs of power cables coming in and out anywhere. We looked at adding a storage drawer for whatever we need, but we can also take that out if we need to access equipment. The other thing we also looked at is a type of rack we wanted to use, and we went, as we are most locations in Lumen Space, they have a high density, extra deep cabinets available, and we went for those 4-post racks. And in the end, these one solution type of racks, we're seeing a draw of about 24 to 28 amps total for all of our equipment. So with that in mind, we were able to take and add, we kind of daisy chained our power controllers. So we have one house power feed coming in. And if we want to expand or we need additional power feeds, we could switch over to 2 powerhouse feeds and we would free up a set of power feeds on the power controller to use at this time. So that's kind of like the high level on how what we've come up with and what we're seeing. On the next slide, so these numbers are based on an amp is somewhere between $15 to $20. Depending on the vendor, that's about where everyone will be, is what we're seeing. So I brought up 2 examples. One's in Los Angeles and one's in Tulsa. In Los Angeles, originally, we had a couple of optical chassis each needing a 60 amp A plus P power draw. We had the half rack router, which was taking 2 60 amp power circuits, our management equipment, which needed a 30 amp AC power circuit. So we were looking at around $3,000 a month in power cost happening. We needed 4 racks for all this, 113 square foot suite space for our cooling needs and everything. We just really ran out of space pretty quickly in there. With the NGI layout, we have 132 slot optical chassis in one rack, and it is a 60 amp power circuit feeding it. And our actual draw now is 41 amps. And that cost is $900 to $1,200 MRC. The packet management equipment needs, we were able to take it from the 2 60 amp A plus Bs and a 30 amp AC power circuit and put it onto 140 amp power circuit. Our actual draw there is about 17 amps. So we're seeing what the cost there is $600 to $800 a month. So we have 2 racks now inside a 96 square foot suite. So we have space available. Our cooling demands are much lower because the equipment is just not taking up as much. We were able to reduce our watt usage by more than 7,000 watts or 124 amps. I mean, for sake of brevity, it did combine DC and AC amps and wattage there. Overall cost savings, as you can see, depending on the vendor provider, it's close to $4,000 a month. In Tulsa, a smaller location, we had 2 standalone cabinets. We had one 60 amp A plus B circuit for the optical, and then we had a 180 amp power circuit for the router and the management needs. So we used up all of that space for hardware, cooling needs, etc. And as you can tell by these numbers, again, they went down quite a bit. So our current draw now is about 32 amps. I'm sorry, we're now at 23 amps. Previously, we were at 32 amps for the optical and 55 or so for the packet management. In 2022, we're going to go back and relook at some of these locations and see where we can even drop our power circuits down lower for additional cost savings. There's just a reduced need of power based on the equipment, based on the type of equipment. We just need less space available. And we've been able to increase safety and sustainability in all of our racks, cabinets, and suites because we were very careful and we were conscientious about how we racked and how we powered up our equipment. Not saying this is like the perfect layout, but it is a really efficient one for us right now. And I think it's going to be helpful moving forward. In all these locations, we have between 2 to 4 RUs of space available where we can add additional equipment or we could. And we also have the power feeds available if we do need to physically augment somewhere. One of the interesting things I heard is a rumor that there's a CDN that is actually copying this type of rack layout, starting at the bottom with their optical equipment, just to use all the rack space possible, keep it as efficient as possible. So that's what I have to cover, and I think it goes back to Jeff.
So just wanted to do a quick summary, and then we're going to move into transition. I realize we're up against some time, but I think we want to run through transition, and hopefully we'll give folks a little bit of a break. But just to do a quick summary, the platform definitely, as built, delivers the baseline NGI services that we hoped it would. We do still have work to do, bug fixes, slight changes in configuration to optimize that. But the bottom line is that it did overall meet those requirements. The good news is that we did have workarounds in place for the things that were lingering, which is why we've gotten to the point where Chris can now talk about service transitions. But yeah, just wanted to cover that, make sure that folks were clear, and that's why we are where we are. Go ahead, Chris.
Yeah, sure. And I'll try and move kind of quickly through this because I think a lot of the folks here probably saw a lot of this content already over the summer and may have been directly involved in it, but I don't want to assume that for everyone. So just a real quick background. One of the core tenets of the migration here was that we would do this in place, that it'd be as with as little as disruption as possible. So one of the very early concepts we came up with was how to transition all of our edge connections in. And there was a feature on the Cisco equipment that allowed us to effectively just pass traffic through from one port to another. So we came up with this concept of shimming the Cisco's in, because when you're working with remote hands in the field and you've got a ton of fibers to move around, and I mean, there are thousands or hundreds of connections for us to move, sometimes even in one specific pop. Doing that work with the logical work at the same time didn't make a whole lot of sense, because if the logical work, moving the BGP session over, if it didn't reestablish for whatever reason, would require us to physically roll back, and that didn't really sit well with us in terms of the timeline we had, the level of effort, the amount of coordination with the field. So we wanted to decouple those two things from each other. So we came up with this concept of shimming, which is effectively moving the edge connection, the port, the fiber that goes out to the connector, moving that from the Juniper over to the Cisco, and then interconnecting that old port that they were on the Juniper to the Cisco as well. So there's basically 2 ports on the Cisco that service a given edge connection. And the Cisco just sits there for a while and just blindly passes traffic through. So we didn't actually have to have like NSO stood up, have all the services ready. We could start that physical migration work before having all that route policy that Jeff talked about done and all the services defined in NSO. So what that did was it paved the way for us to, instead of having to have work in the field and roll hands in the field, just sit at a keyboard and remotely move things. So Chris, if you want to move to the next slide, I'll talk a little bit about the BGP migrations, and then I think AJ is going to talk about OESS, and Jeff's going to talk about the I2PX peers. So next slide, Chris. It's not advancing for me. I don't know if it's moving for anybody else.
No, my window disappeared. I apologize, everybody. Give me 1 second.
Well, while Chris is bringing that back up, I'll just kind of talk through some of the major things on the slide. So, you know, we had to kind of divide our work up into a couple of major phases. And then you can think of there were kind of three major transition pieces on the layer 3 network, and this is not optical. There were edge facing connections that had nothing to do with I2PX. So that was all of our connections out to the connectors, our peers, and a couple of other miscellaneous. Then there was OESS services on top of that. So you have the BGP, the layer 3 connectivity, the OESS circuits, and then there's the I2PX. So we kind of divided those into three main areas. And I'm just going to talk about the first class, which are the BGP sessions facing the community edge. And there were roughly 800 of those to migrate. We had, you know, this says we did this over the course of 30 days. It really was about 2 to 3 weeks for the majority of them. We grouped those by router. We started with the smaller routers first. And then in some cases, we would combine multiple routers in a night. We scaled it up as we went. So as we were getting comfortable with the process of migrating, you know, one of the big questions we had initially was, how long is this really going to take? We had all this theory about how it was going to work. But it was like, you know, once we get started on it, are we going to start running into incompatibilities or, you know, just weird config things that we miss, whatever. Thankfully, that wasn't a huge deal. And we were able to ramp up. We've ultimately ended up, I think on our most busy night, we moved like 170 BGP sessions in one night, which was, you know, the very last night or something like that. But, you know, we were always kind of working towards that. So we started out with like 4 sessions a night, ended up with about 170 sessions a night. And the way we did that was, I mean, we could not have done that without all that automation stuff. And the NSO config stuff that Jeff had already talked about. And there's gonna be a whole slew of talks about that tomorrow. So if you're interested in diving into this a little bit more detail, please attend that, ask questions there. But what we effectively did was, prior to each migration, we looked at all the BGP sessions on the legacy router. We had some scripts that scraped all the Juniper config, helped us find where there were exceptions to be made in the route policy, helped us translate the route policy into the NSO language that got pushed out to the Ciscos. We were able to push everything out and have it all pre-staged and ready to go during the migration window. So then during the migration window, all we really had to do, I'm hand waving here for the engineers that were involved in this, they're probably cringing here, but all we really had to do was hit a couple buttons and you know, the NSO took care of it. The Juniper, we had scripts to tear things down there. So one of the things we were worried about as we were running through this was how do we verify that we're not going too quickly and that we're not breaking things as we go. So what we did was wrote a series of scripts that used some Cisco libraries to the PyATS, if anybody's familiar with it, to do some state some state gathering before we did the migration. So go onto the Junipers, look at all the BGP sessions you're going to migrate in some chunk, some reasonable chunk, like 10, let's say. And then grab all the routes that are advertised, the number of routes and the actual list of routes themselves. And then once you've migrated the BGP session to the Cisco router, rerun that script against the Cisco And then it would dynamically compare those two things together, and it would tell us, okay, before we moved, you had 2 extra routes that aren't for some reason not making it now. And we would do that right before the maintenance and then right after, so that there was no chance that things had changed. And that was pretty helpful in terms of being able to identify those things as we went. So what we had was, during these windows, we had 2 engineers effectively. We had one engineer that was doing the keyboard work to do the migrations, and then we had another person that was paying attention to all those validations. And that system actually worked really well for us. Additionally, we had Zoom windows or Zoom bridges stood up so that the connectors that were being migrated that night could join and let us know if there were any issues. And we really encouraged people to do that, to make sure that we didn't miss anything ourselves. So there's a lot of effort to put into doing this in a way that didn't provide any lasting disruption. Each migration took, each BGP session migration, we would drain the traffic with some of that maintenance mode stuff Jeff talked about but we would do that on the Junipers, drain the traffic away, and then standing it up on the new network. You're looking at 5 minutes or so of downtime in most cases. So I think ultimately it went really well. There were a little bit of behind the scenes, like some Scotch tape and stuff, putting things together, but ultimately I think it went really well. And we didn't have any huge major disruptions. So that's the method we took for that. AJ is going to talk next about how we did the OESS migrations. And there's a lot of similarities in terms of the philosophy there. So AJ, do you want me, are you ready to chat?
Yeah, I'm ready to go.
Awesome. All yours.
Yep. So I figured I'd start off with, for people who weren't aware, that we had to first do some OESS or Cloud Connect software transition, right? So I put out here what kind of our requirements were when we first started, which was that the OESS or Cloud Connect tool must support both the old network and the NGI network simultaneously, as well as provide a migration mechanism between the 2 networks. This was obviously because we wanted to do an in-place migration. One of the other things was that the migration process should support individual connection migrations instead of a single flag day. We totally could have done a single flag day. We could have just done a whole bunch of scripts against the database and just said magic has happened and now everybody is running on the NGI network, but nobody likes that idea because it's hard to tell what's not working at that point once you do that. And then the last one was really that the OESS provisioning for NGI has to go through the NSO system. So those were kind of the 3 main requirements that we had to work with. So our solution here was basically in the back end of OESS, we added support for another controller type for NSO. The thing is, this is probably the 3rd time OESS has had to do some kind of migration, and the 2nd time we've had to do basically a major technology migration, let's say. So we already had a bunch of support to kind of do all this stuff baked into the database. So if you remember, we did OpenFlow to MPLS migration probably 6 or 7 years ago now. And so, basically this was pretty easy. We just had to add what we call a driver to OESS to be able to talk to NSO. And so this basically allowed the two networks to operate in OESS as kind of ships in the night. You could provision on the Ciscos or you could provision on the Junipers, but you couldn't provision Cisco to Juniper. So they were ships in the night, but both were working simultaneously. And so this was actually in OESS version 2.0.13. So you guys can go out there and find that release if you're interested to see what we did. One of the things we needed to do was NSO needed 3 models from us. So they needed the equivalent of the L2 VPN, the point-to-point layer 2 provisioning. L2 VPLS or multi-point. I don't think it's actually L2 VPLS right now, but essentially we needed a multi-point template that would handle layer 2 provisioning with 3 or more endpoints. And then we needed the L3 VPN template, and that was just for OESS to interact with NSO. And then we utilized the OESS ACL system to control when the migrations would take place. So we could basically stage the migration. So for a while, we had the Cisco's or added to the OESS system, just nobody else could provision to them. But we could change ACLs around to allow us to do testing on the production network before we actually did any migration. So we were able to kind of test the whole system before we actually started migrating people to it. And then basically the idea here was after that, each OESS connection would be migrated to to its NGI ports individually. Go ahead and next slide, Chris. Okay, so kind of following in the same kind of thing that the other guys have talked about here. We had essentially 800 customer created connections that needed to be migrated. Almost 100 of those are Cloud Connect related sessions. So, that was kind of a lot of work. One of the other tricks to remember here too is for most of the layer 2 stuff, we have zero visibility into if it's working or not. So all we could really take a look at was traffic before and traffic after. And, so that it wasn't exactly useful for us to be able to tell if things were working. With the BGP peers, we could mostly tell for our L3 VPNs. The maintenances were grouped by work group and connections. So we actually had a spreadsheet and we kind of broke everything out and had an ordered list of circuits that we were doing each night. Essentially, the numbers we came up with was we could do a maximum of 170 connections per night. And this led to like 12 nights of maintenances. And the reason for that was basically we put a time period in that we wanted to wait between each circuit migration. So that way, if we were doing like 2 work group related things right next to each other, that you would have one of your connections come back up before we did the next one. So there was at least a 2-minute interval to prevent that disruption for customers. So the process, well, the first night was basically we migrated all the ACLs from the old network to the NGI network. So no actual traffic changes or anything like that. This was just changing the ACLs. And what this does is it makes it so that way all future provisioning, anything happening after that point, would happen on the NGI network. But all of existing traffic, all existing connections on the Juniper network still existed. So then nights 2 through 12 were when we did the actual migrations. And basically for each connection, we had a script that would review the endpoints. It had the mapping of the old endpoint to the new endpoint. And we would basically use the OESS API to make an edit call. And that would basically remove it from the old network and add the new endpoints on the new network. And there's a few reasons why we did this. One of the important things was that the names, history, and permissions all remained the same throughout OESS. So if you guys had a circuit that existed before, or a connection that existed before, all of the history, the name, the permissions, everything is still there. So we kind of were able to kind of do all of that data in place as well, which was important for us. The result here is I think we did 98% of all the connections in OESS that were migrated. The remaining connections are either being manually migrated because there was no shim involved, or there's some little minor technical things, or there are a bunch of old test paths, all kinds of stuff from when we were doing testing before that exist on the old network that we're just not migrating over. So yeah, we were able to complete all of that. It took, like I said, about 12 nights. We split it between really myself and Jonathan Stout, who's kind of the lead now on OESS. So between the two of us, we had a lot of late nights there. The maintenance window was basically midnight Eastern to 8 a.m. And so we tried to do everything in that period of time. So it was a long few weeks, but we managed to get it all done. I think that's it for me.
Great. I'll just touch real quick on the service transitions that we had to make for wave services. So I always like a good visual picture. So this is a visualization of the wave services that we're running under AL1S for the community. These were a mixture of 10 gig and 100 gig services, all wave, what we would call wavelength. And so in this case, the red links are all 10 gig waves and the green links are all 100 gig waves. And every single one of these had to be migrated from the muxponder-based 10 gigs, which are not supported under a flex grid system, to e-motors and wave servers. And the green links needed to be migrated to either side channels, what we kind of flippantly call side channels, or meaning the capacity on the wave server 5s, or their own discrete transponders. So I just wanted to kind of click through this and just talk about the scale of this. So there were 19 community 100 gig waves, 41 10 gig community waves, all that needed to be migrated. For the 100 gig waves, there were 10 maintenance windows that had to be scheduled. Down here in the common factors, every single one of these required a tech to be present on the A and Z side, required hardware to be pre-staged, tested. A lot of times they required fiber termination changes, much like the shims that we had to go through. And so all of these required a large amount of coordination and execution for them to be successful. And the cost for missing these executions is relatively high, weeks of time, hundreds of dollars in field service requests. And so I really was proud of the team. Almost all of these went off without a hitch once the hardware was in place and the circuits were tested. And these are all complete. We've got a few community circuits on the West Coast that we're still working on that are sort of special infrastructure sharing applications. But for the wave services that are provided by the platform, these are all complete, and we've moved on to the next thing. So big props to the team on this. And I'll hand it over to Jeff. We're right at time, so we'll try to get through our last few slides, and we want to go through peering migrations and then sort of a wrap up on forward-looking items, and hopefully everybody can have a little break. Go ahead, Jeff.
Okay, trying to go through these really quick then. We had just over 900 BGP neighbors to migrate for I2PX and NetPlus combined. So while the rest of the team has been focusing on participant-facing connectivity, I've been spending the last 3.5 months working on migrating all of these connections. I guess a big difference is, if we go on to the next slide, is with these connections, they are single purpose for the most part. And so that allowed us to approach this differently. We did not have any of these shimmed. Instead, we relied on the fact that we interconnected the two networks together, and that we had layer 3 interoperability between the old MX network and the new NGI network. And so we can move up here at any time from the old network to the new, and we don't need to be concerned about doing that, because traffic will flow over the interconnects that we created between the networks. And so we did approach all of these as hot cuts. And so we basically moved from POP to POP, and took an approach of, for each BGP neighbor we needed to migrate, or each private connection we needed to migrate, we shut down the V4 and V6 neighbors with that peer. We waited time for the traffic to drain. We removed the interface configuration from the MX router. Step that I missed in here is that we're working with remote hands to do all of this work. So on a conference bridge, and we tell the person who's in the facility, please move the patch cable from this port on the MX router to these ports on the NGI routers. And that might be a single interface being moved, or for lags, it might be multiple physical interfaces that need to be repatched at the same time. Once that's done and we confirm we have link, then we enable the service in NSO, which deploys the interface and BGP config for us. We confirm we have success, BGP neighbors have established, routes received, and then we repeat. And we go through that for all of the peers at a particular location. Next slide. These are the main metros where we were doing this work. We categorized them in two different ways. Some of them were simply an equipment transition where we had the MX router and the Cisco 8000 NGI routers sitting in the same cabinet or neighboring cabinets. And it was simply a matter of moving a patch cable between those. For Ashburn and Los Angeles, we actually completely moved to different facilities. Ashburn, I'll clarify, Ashburn, we moved cages within the facility, but it's essentially the same amount of work. That all of the cross connects that we have in the old space need to be basically migrated to the new space. And so that's a much more involved process. While we've completed the migration of all of these peers at a layer 3 perspective to NGI, both Ashburn and Los Angeles, we are still using our old Juniper equipment to aggregate some of those peers that haven't been migrated yet, and then trunking them to the NGI equipment. But all layer 3 routing is now on NGI for those. And we're using the NGI backbone for all I2PX and Net Plus traffic. Next slide. This is a graph showing the migration over time. The green line on the graph is what I've just been talking about, the approximately 850 I2PX BGP neighbors. So starting around August 23rd, I think it was, we started with our first migrations in Chicago. And then as we progressed, and we're now down to basically 0 neighbors left on the MX network. The purple line shows the work that that Chris was talking about earlier with the shimmed migrations of participant connections. So there you can see that the participant migrations started at the end of August and progressed over time, most of them happening in the first couple of weeks of September. Next slide. Just yet another view of the same migration work that I've been talking about, this time looking at the private connections, showing the green line over time as connections were removed from the MX network, the gold line showing as interfaces were being added to NGI. Next slide. And just yet another view of traffic ingressing on the MX network versus the NGI network on the right. And so by the time we reach the end of November, everything's transitioned from the MX to the NGI network traffic-wise. Next slide. One other thing I just wanted to touch on as I wrap up. This summer, looking at the I2PX public exchange connectivity across the country, we had 100 gig connectivity already in Seattle, Chicago, and Ashburn. As part of migrating to NGI, I worked with the providers of the remaining exchanges, next slide, to augment all of those to 100 gig also. And so we're now 100 gig at all of the exchanges where we see we're going to have long-term growth. Equinix Palo Alto is an exchange that we're migrating away from. All new peers are turned up at San Jose, but we're just keeping the 10 gig there for peers that we aren't able to connect to in San Jose. And that wraps up what I had.
Thanks, Jeff. You know, I won't go through this entire slide, but when we post the deck, folks can look at it. Just some challenges that we see for 22 and beyond. Cleaning up lingering platform issues, new service implementations, lots of enhancements to existing services. We have a backlog of community requests for both for the entire platform, layer 1 through layer 3, that we'll be working on. 400 gig turnups, excited to get to that. Rob touched on a few of the sort of key initiatives, which are Northern Tier and Exchange Point, along with, reviewing our process for overlay networks and mission-specific VPNs. Really going back to those principles of making the platform extensible and accessible for a variety of community applications. Definitely be our focus. And felt like I needed to give yet another bump to our team. Sustained effort over many years, 2016 through today. I'd like to think that it was kind of a marathon pace through 2020, and then it turned into a sprint through 21. It was a lot all through that entire arc. I just wanted to mention that, again, what's presented here is just a tiny fraction of the total work that went into making this happen. We only had an hour and we've already gone 10 minutes over, and we could have probably gone on for another hour. So, we'll try to make sure that some of this content pushes out over the next 6 months through webinars and other talks at other meetings. I did want to just say the project also was successful because we had comprehensive project management, both internally at I2 and as well as in Sienna and Cisco GDT land, as well as Lumen. So, props to the project managers and all the folks behind the scenes there.